Hi, in this video we are going to continue our discussion of eigenvectors and eigenvalues, expanding their basic definition into the concept of the eigenvalue decomposition. Let's begin with a reminder of what eigenvalues and vectors are and how we compute them. Eigenvalues and eigenvectors are scalars lambda and vectors x that satisfy this relationship for a matrix. A times the scalar, so the vector x, gives a scalar multiple of this. A scalar and vector that satisfy this are eigenvalues and vectors of the matrix A. This only applies to square matrices, and for an n by n matrix, we always will have at least one and at most n eigenvalues. We find the eigenvalues as the roots of the characteristic polynomial, this determinant of lambda I minus a, where in this context, lambda is a variable. We derive a polynomial in lambda and solve for the roots of that polynomial. Once we have solutions, we have a set of lambda I that are just numbers. Those numbers can be plugged in to the same matrix expression, lambda I minus a, and the null space of those matrices, one for each eigenvalue, gives us the eigenspace associated with that eigenvalue. It's a vector space. Vector spaces are characterized by a basis. The null space basis are the special solutions to the appropriate homogeneous system, and this is how we characterize an eigenspace. We will always have at least one vector in this basis, because if this is a non-singular matrix, a singular matrix characterized by a zero determinant, it must have a null space of dimension at least 1. Now we're going to go into our first really important point. It's a slightly busy slide. I'm going to walk through this. The key take-home message is simply in the title here, though. The eigenvectors of different eigenvalues are always linearly independent. How do we know this? This isn't quite a formal proof, but it is the beginnings of one. Imagine that we have 3 eigenvectors, an x1, an x2, and an x3, that have corresponding eigenvalues, lambda 1, lambda 2, and lambda 3. This simply means that each of these pairs, lambda 1, x1, and so on, satisfy the appropriate eigenvalue equation for matrix A, for the same matrix A. Now, let's consider the case where x2 happens to be a scalar multiple of A, of x1. What we will see is that if 2 eigenvectors are scalar multiples of one another, they have to have the same eigenvalue. We can derive this result quite simply by defining x2 to be some scalar multiple of x1. Then we start with our equation a times x2, substitute in this result to give x2 is k times x1. This gives us k a times x1. But ax1 by this eigenvalue expression has to be lambda 1 x1, and so we substitute that here. What we then, however, see is that k times x1 is, of course, x2, so this becomes lambda 1 times x2. But from this eigenvalue expression, a times x2 has to be lambda 2 times x2. We have the same vector on either side. If a scalar multiple of the same vector is equal to itself, the eigenvalues have to be the same. We can extend this idea. Imagine that we have these 3, and we can find that we derive that if these 3 are linearly dependent, but not scalar multiples of one another, they again have to have the same eigenvalue. We start with writing x3 as a linear combination of x1 and x2. It means they're a linearly independent set. We begin with ax3, and again substitute ax3 with this linear combination. This gives us k ax1 plus l ax2. The same way, ax1 becomes lambda 1 x1, ax2 becomes lambda 2 x2. And we have this relationship that can be written here. However, we can equally expand this x3 with this same scalar multiple, okay? And that gives us the same left-hand side here as we do in this equation, but a new right-hand side. And what we see here is, if we look closely, there's a term that has a k and an x1 and a k and an x1, and a term that has an l and an x2, an l and an x2. We move everything over to one side and factor out that kx1 and lx2, and we're left with this result here. A sum of a scalar multiple, remember lambdas are just numbers, and the k is just a number, of x1 plus a scalar multiple of x2 has to equal 0. Now, we've already said that these are not scalar multiples of one another. Right? If they were, if x1 and x2 were scalar multiples of each other, they would have to share the same eigenvalue. Right? And we're trying to look for the more general case, so we've assumed that they're not. If they're not, then we can't get 0 simply by taking a sum of scalar products of the two. Which means the only way we can get 0 is if each coefficient is 0. How can each coefficient be 0? That's only true if lambda 1 equals lambda 3 and lambda 2 equals lambda 3. That is, lambda 1 equals lambda 2 equals lambda 3. If you haven't internalized this proof, that's fine, or this beginning of a proof. We actually need to extend this to the case where we have more and more possible linear combinations. That's not a big deal. You'll have opportunity to explore this in the book a bit more. However, please try to remember the take-home message that eigenvectors of different eigenvalues are linearly independent. All right. Why is this important? Well, we know that if an n by n matrix has n distinct eigenvalues, that is n different eigenvalues, the largest number that it can have, each eigenvalue has to generate at least one eigenvector. We know that to be true. If they're all linearly independent, that means that we have a total of n linearly independent vectors. These are vectors that come from an n by n matrix. So they are have to be vectors that live in Rn. We can't have more than n linearly independent vectors. This tells us two very important things. First of all, that each of these individual eigenvectors has to be generating exactly one linearly independent eigenvector. But more importantly, perhaps, the set generated by taking one eigenvector for every eigenvalue is a basis for Rn. It's a set of n linearly independent eigenvectors from Rn. That is a basis for Rn. So when we have n distinct eigenvalues, the set of all of the eigenvectors spans the entire parent space. This means, of course, that we can express any vector as a linear combination of those. Right? But what else can we do? Well, let's again consider this special case where we have n distinct eigenvalues. And let's call those lambda 1, lambda 2, and so on. We'll have n of these, and these are all different numbers for some n by n matrix. And each of these will have an eigenspace that's a line. We can take any vector on that line, any eigenvector corresponding to each of these eigenvalues. This will be a set of n linearly independent vectors. Each of these has to satisfy our basic eigenvalue equation of AXI equals lambda IXI. And we can express this general rule in a matrix form, where we combine all of the xi's into a matrix whose columns are those eigenvectors, and express the left-hand side as A times the matrix X. And we can combine all of the eigenvalues into a diagonal matrix, a matrix that only has non-zero entries on the diagonal, and the diagonals are those eigenvalues, making sure that the order is the same, x1, x2 to xn, lambda 1, lambda 2, and so on to lambda n. And x times lambda will give this right-hand side. Why is this the case? Let's just walk through it to demonstrate that this really will work. A times this matrix X, this matrix of eigenvectors. We propagate the matrix multiplication into each column. A x1, A x2, A xn, so on. Which, of course, since this is one part of the eigenvalue equation for each of the eigenvectors, can be replaced with lambda 1 x1, lambda 2 x2, and so on. A times x gives us a matrix of left-hand sides, which can be substituted with the appropriate right-hand side. What about x times lambda? Well, x times lambda, we have this same matrix whose columns are the eigenvalues. Multiply it by a diagonal matrix. When we multiply a matrix by a diagonal matrix on the right, the effect is that we multiply each column by the corresponding diagonal entry. And you can sort of see about this. We multiply the first, each row of this matrix by the first column. That first column is going to pull out only the first entry from every row. If we multiply each row by the second column is going to pull out only the second entry in every row and scale it by the appropriate piece. So this product also gives us lambda 1 x1, lambda 2 x2, and so on, the same result as AX. That means that AX equals lambda x lambda, and this encapsulates this relationship that AX, sorry, and there's I'm missing lambda I in here, lambda AXI equals lambda IXI for every I. All right. Now, this is just simply right now a matrix equivalent of the eigenvalue expression. Let's see what we can do with this. I'm sorry, the same typo is here, so I'll put this lambda I. X is a matrix whose columns are the eigenvectors. We know that there have to be n of those, and we know that they have to be linearly independent. We have a square matrix with linearly independent columns. X is always non-singular. Lambda is a diagonal matrix whose entries are corresponding eigenvalues. It won't always be non-singular. It will be non-singular only if all of the eigenvalues are non-zero. If any of the eigenvalues are 0, then there's a diagonal entry with 0, and lambda won't be singular. The important piece here, however, is that x is non-singular. And if x is non-singular, that means that we can take this general matrix expression and we can multiply both sides by the matrix inverse. X inverse gives the identity matrix, leaving us only A, and we're left with a right-hand side of x times lambda times x inverse. We could equally have started with ax equals lambda x, ax equals x lambda, and multiplied both sides on the right by x inverse. And this would give us lambda equals x inverse ax. This general result, expressing A as a product of 3 matrices, one of which is a diagonal matrix, one of which is an orthogonal matrix, is what we call the eigenvalue decomposition. Right? It's a way of breaking up a matrix A into a product of other matrices that have special features. In this case, the special features are that x has to be non-singular and lambda has to be diagonal. All right. Now, that derivation was based on the idea that we have distinct eigenvalues. We've seen that in some cases, a square matrix may not have n distinct or different eigenvalues. Some of the eigenvalues can be repeated when we factor our characteristic polynomial. That is, we get terms that are squared or cubed or higher powers in our characteristic polynomial, meaning that that term will give the same eigenvalue. These repeated eigenvalues may not generate more than one linearly independent eigenvector. They might. Sometimes a repeated eigenvalue will generate more than one linearly independent eigenvector. The eigenspace will have dimension more than 1, but in some cases, an eigenvalue might be repeated, and it might still only give an eigenspace of dimension 1. These ideas lead to 2 definitions. One, something that we call the geometric multiplicity of an eigenvalue. The geometric multiplicity is simply the dimension of its eigenspace. Remember, for any eigenvalue, we can write down a matrix, lambda I minus A, and this will have a null space, a set of solutions to this system, the homogeneous system. The dimension of the null space for this system is the geometric multiplicity of the eigenvalue. Every eigenvalue has to have a geometric multiplicity of at least 1, but when the eigenvalues are repeated, it can have a higher multiplicity. It can have a higher dimension for the null space. The algebraic multiplicity is the number of times that eigenvalue is repeated when we factor a characteristic polynomial. Right? So let's imagine that we had something like that this characteristic polynomial gave us a factor of x minus 2 squared times x minus 1 cubed. This would have 2 eigenvalues, an eigenvalue of 1 and an eigenvalue of 2. The eigenvalue of 1 would have an algebraic multiplicity of 3, and the eigenvalue of 2 would have an algebraic multiplicity of 2. Right? This is what we mean by geometric multiplicity, algebraic multiplicity. Let's go through a couple of examples to get us a feeling for this. Let's take the example of A, given this matrix here. This is one of the matrices we looked at in a previous example for computing eigenvalues and eigenvectors, I believe. When we look at this matrix, we can compute a characteristic polynomial. We have lambda 0, 0, minus 0, 1, negative 1, 2. This gives us lambda minus 0, negative 1, plus 1, and lambda minus 2. We compute lambda times lambda minus 2 minus 1 times negative 1. This gives us, when we factor this out, lambda minus 1 squared equals 0, giving us one eigenvalue with a algebraic multiplicity of 2. A 2 in this factored breakdown. When we plug lambda equals 1 into this expression, we get a matrix of 1 minus 1, 1 minus 1. A single step of elimination takes us to a reduced row echelon form with a single pivot and one free variable. We set the free variable equal to 1 and pull out the pivot value from our reduced row echelon form to give us one basis vector. The eigenspace associated with this eigenvalue is one-dimensional. It has a geometric multiplicity of 1. They are not the same. If we take another example, let's take this matrix 3, 0, 0, 3. Actually, this happens to be a diagonal matrix. We do the same thing. Lambda 0, 0 lambda minus 3, 0, 0, 3 gives us lambda minus 3, 0, 0 lambda minus 3. Product of the diagonals minus the product of the off diagonals gives us actually a characteristic polynomial that is already factored. It's clear that this will be equal to 0 only when lambda equals 3. We have one eigenvalue, and once again, its geometric multiplicity, its algebraic multiplicity is 2. The same as the case before. But now, when we plug 3 into this expression, we actually get the 0 matrix, which is a little bit interesting. 0, 0, 0, 0. The 0 matrix is a reduced row echelon form, right? But it's one that has all free variables. There are no pivots. 2 free variables generate 2 special solutions. The eigenspace associated with this, the null space of the 0 matrix, is all of 2-dimensional space. We have a 2-dimensional null space. The geometric multiplicity is also 2. Because we have a geometric multiplicity of 2, 2 linearly independent eigenvectors, these span all of R2 space. This leads us to an ability to generalize the eigenvalue decomposition beyond the case of having distinct eigenvalues. And we do this in the following way. If we have a square matrix that has n linearly independent eigenvectors, right? This is the key point. As long as we can find n linearly independent eigenvectors, we can do this. We let x1 and so on be a set of these linearly independent eigenvectors, and the lambdas are their corresponding eigenvalues. By exactly the same logic as we saw before, the eigenvalue equation can be written in matrix form with exactly the same set of rules. X is a matrix whose columns are the eigenvectors. Lambda is a diagonal matrix whose entries are the corresponding eigenvalues, where the only difference is that these eigenvalues are not all unique. If any eigenvalue had a geometric multiplicity of more than 1, what does that mean? It means its eigenspace had dimension more than 1. It means that some of these eigenvectors in this linearly independent set have the same eigenvalue. And all that means is that that would be repeated in this matrix, that we may have the same eigenvalue appear on the diagonal. As long as we have n linearly independent eigenvectors, we can do this. But if we don't, if we ever have a case where we have fewer linearly independent eigenvectors than n, we will not be able to write this in the same way. All right. So, to summarize our general eigenvalue decomposition, any n-square matrix A with n linearly independent eigenvectors can be expressed in this form, where X is non-singular with columns as eigenvectors, and lambda is a diagonal matrix with the eigenvalues. Any matrix that has this form, that can be written in this way, we say is diagonalizable. Why do we use that term? We use that term because lambda is a diagonal matrix. We can express A in terms of diagonal matrix like this. Because of this, we often, you'll come across the term diagonalizing a matrix, which means the same thing as performing an eigenvalue decomposition. All right, just a couple of terms here, nothing different in terms of the method that we use. All right, what use is the eigenvalue decomposition? Why does it help us to do this? Remember, we began our discussion of this unit reminding ourselves that the LU decomposition and the QR decomposition are able to speed up the types of calculations that we need for systems that are expressed in the form of AX equals B. And we asked, can we do something similar for systems of the general form AXI equals XI plus 1? And remember that this form also leads to A to the K XI equals XI plus 1, XI plus K. Right? Can we speed up the types of evaluation in this system using the eigenvalue decomposition? Let's begin thinking about matrix powers. Matrix powers can be expressed, what does it mean to be a matrix power? It's just multiplying the matrix A by itself k times. We can just think about repeating a matrix multiplication k times. And if A has an eigenvalue decomposition, then we can substitute this expression into each of these pieces. Again, writing out this k times. But let's take a look at what this product gives. Every neighboring term has an x inverse times x, but x inverse times x equals the identity matrix, which we can remove from the expression. What this leads to is lambda, and so on. And the only ones that we are not able to remove in this way, the ones that we are not able to remove are the very first entry of x and the very last entry of x inverse. So this xa ends up being x times times lambda times lambda times lambda n times, k times multiplied by x inverse, which is just x lambda to the k times x inverse. Why does it help that we can write this? Essentially, writing something that looks very much like the original eigenvalue decomposition, but replacing the lambda with lambda to the k. It matters because lambda to the k is a really easy thing to do. When we have a diagonal matrix raised to a power is simply the diagonal matrix whose entries are raised to the power. So instead of having to do matrix multiplication repeatedly, we have to simply take a scalar power n times. This greatly reduces the amount of calculation involved in evaluating this a to the k. What is another benefit of this? Let's consider our form AXI equals XI plus 1. Again, we're going to start with our original form and think about how can we manipulate this. Let's take our original form here and multiply both sides by x. Certainly can do that, and this will give us an expression x times a times x1 equals x times a I plus 1. Now what I'm also going to do is I'm going to note that I equals x inverse times x. And I can always insert an identity matrix. So I can take this and I can insert it into this position here. Multiply a by the identity matrix, always allowed. This then gives us an expression that looks like this. Right? I've just added in this piece that is equivalent to the identity matrix. Why might we do this? Well, then we can take this first piece, x times a times x inverse. This is simply lambda. And what do we now? We have lambda x times xi equals x times xi plus 1. If we make a definition of an x hat, say let's call x hat simply x times xi, then our AXI equals xi plus 1 becomes lambda xi hat equals xi plus 1 hat. Why is this helpful? Well, this product, lambda times xi hat, is very easy to compute. When we have a diagonal matrix multiplied by a vector, all we need to do is multiply each term of that vector by the corresponding eigenvalue. Matrix multiplication is expensive. Diagonal matrix multiplication is cheap, which means if we want to evaluate a sequence of these, we can start off by converting our starting vector into a version x hat, and then do everything we want using lambda instead of a. Anytime if we want to go back to our original form, you might say, oh, well, but this gives us lambda hat, or x hat. It doesn't give us the x that we wanted. we can always convert this back, remembering that X is a non-singular matrix, and so Xi can always be found as X inverse times Xi hat. So we have a way to reverse this translation. Right? In the language of kind of linear mappings, what we are really doing is we're moving ourselves into a coordinate system where we can do everything with a diagonal matrix and then moving back into our original coordinate system. I'll discuss this in an optional video later on. All right. I want to end our discussion here with one last really important result, something called the spectral theorem. We've seen that eigenvalue decompositions can be useful. They can speed up matrix powers. They can speed up the evaluation of the kinds of products that we see in dynamical systems and Markov chains. But not all matrices are diagonalizable. Some matrices have an incomplete set of linearly independent eigenvalues. Some matrices are diagonalizable but have complex numbers, which makes things messy. When we're dealing with symmetric matrices, matrices whose transpose is equal to themselves, symmetric matrices have some very, very interesting properties. First of all, they are always diagonalizable. The eigenvalues always have a geometric multiplicity equal to the algebraic multiplicity. We never end up in this situation where we don't have n linearly independent eigenvectors. Symmetric matrices also always have eigenvalues that are exclusively real numbers. We never get complex eigenvalues when we're dealing with symmetric matrices. Finally, for symmetric matrices, it's not only the case that eigenvectors corresponding to different eigenvalues are linearly independent, they are in fact orthogonal. This last point is really interesting because it means that we can construct not only a linearly independent set of eigenvectors, but an orthonormal set of eigenvectors, an orthonormal basis for Rn. Right? If we can do that, then instead of a general X that has eigenvectors, we have a matrix Q that has orthonormal eigenvectors, Qi dot product with Qj equals 0 for all pairs, and that their dot product with themselves is equal to 1 for all I, orthogonal and normal. And when we have a matrix that has orthonormal columns, its transpose is equal to its inverse, and that lets us write the eigenvalue decomposition in this special form, A equals Q lambda Q transpose, where Q has orthonormal columns. And we don't need to take the inverse, we just need to take the transpose. Important to note that although we always can write this form, we have to be careful about doing so. We have to make an effort to. In order to write this, we need to construct an orthonormal basis for each eigenspace. This often is an easy thing to do when we have eigenvalues that are distinct, that have an algebraic and geometric multiplicity of 1. All this means is we have to divide them by their norm so that we get a matrix with a norm of 1. Only the normalization step, very, very straightforward. But when we have eigenvalues that give rise to a 2-dimensional or 3-dimensional eigenspace, we need to apply something like Gram-Schmidt to get our orthonormal vectors. We have all of the tools to do this, however. It's simply a matter of applying it rigorously. In an accompanying worked example video, we are going to go through some worked problems using the eigenvalue decomposition to solve problems, and this will also involve us getting exercises in actually computing the eigenvalue decomposition. There will also be some practice on this in the homework. I will also be adding an optional conceptual video that talks a little bit more about how these ideas of diagonalization can be related to concepts of linear transformations in general, and some other more abstract ideas. Thank you, and goodbye.